될 것 같아. 안 건드릴게. 네. Welcome back to the closing keynote session. The closing keynote speaker is Professor John E. Hopcroft, who is ACMAM Turing Award laureate and IBM Professor of Engineering and Applied Mathematics of Cornell University. Professor John Hopcroft was honored with the ACM Turing Award in 1986. He is a member of the National Academy of Science, the National Academy of Engineering, a foreign member of the Chinese Academy of Science, and a fellow of the American Academy of Art and Sciences, the American Association for the Advancement of Science, the Institute of Electrical and Electronics Engineers, and the Association of Computing Machinery. In 1992, he was appointed by President Bush to the National Science Board, which oversees the National Science Foundation and served through May 1998. From 1995 to 98, Professor Hopcroft served on the National Research Council's Commission on Physical Sciences, Mathematics, and Applications. His research centers on theoretical aspects of computing, especially analysis of algorithms, automata theory, and graph algorithms. Professor Hopcroft is serving as an advisory board member for university in China, Shanghai Jiaotong University, Peking University, and Huazhong University of Science and Technology. Professor Hopcroft will give a keynote speech on needed planning for AI and the information revolution. Let's welcome Professor John Hopcroft with a big round of applause.
Civilization has undergone an agricultural revolution, an industrial revolution, and now is undergoing an information revolution. The information revolution will make many changes in our lives. Jobs will change from manufacturing to information processing, and this will require creating high-quality talent for the information age. In the past, what made nations great was oil, gold, or agriculture. In the future, it will be talent. One of the top priorities of a nation will need to be in improving education. AI will be an important component of the information age. AI will be applied to agriculture, biology, medicine, manufacturing, and many other areas. It will be a major contributor to creating jobs, increasing a nation's gross national product, and improving the lives of citizens. Research has become mathematically sophisticated, and in the future will be even more sophisticated, requiring highly educated talent. I will discuss what China is doing, but first I want to talk about current AI research to impress upon you the importance of focusing on the creation of talent. An important question in the information age is why a network trained on one set of data works on a different set of data. This is called generalization. For an algorithm to perform well on data not yet seen requires two conditions. The training data looks like the full data, and that the algorithm is simple. Otherwise, overfitting occurs. The two conditions will ensure a trained algorithm performs well on new data. Well, consider a hypothesis of a trained program that memorized all elements in the training set that are in the target concept and predicts positive only on these. There will be zero training error, but probably terrible true error. To prevent overfitting, we want our algorithm to be simple. And simple means that our algorithm can be trained to only a small set of hypotheses. We need the training set to be large enough compared to the size of the set of hypotheses so that with high probability, all hypotheses will have training error close to the true error. Then if we find a hypothesis with low training error, with high probability, it'll have low true error. For any epsilon greater than 0, as long as the training set is large compared to 1 over epsilon times the logarithm of the size of the set of possible hypotheses, it's unlikely any hypothesis with true error greater than or equal to epsilon will have 0 training error. What this means is that with high probability, that any hypothesis our algorithm finds that has 0 training error will have low true error. Generalization works in areas other than machine learning. One such area is sampling a data set to get good approximate answers to questions. How large a sample set does one need in order to get good approximate answers? The same theory that explains generalization in learning answers the size of the sample needed for good approximations with large data sets. Suppose one wants to sample large data sets and wants good approximate answers to questions. How large do the samples need to be? Well, this depends on the class of questions one wants to ask. Consider a database where one has the salary and age of every individual. If one only asks how many individuals have age in a given range and a salary in a given range, we refer to the questions as rectangular. If one has the locations of every taxi in Seoul and wants to know how many taxis are within 1 mile, they're asking a circular question. To determine how large a sample needs to be in order to get a good approximation with high probability requires the complexity of the set of questions that will be asked. Thus, we need a measure of the complexity of sets of questions. And this is what corresponds to the size of the hypothesis class in machine learning. One measure of complexity is called VC dimension. To define VC dimension, I first need to introduce the concept of shattering a data set. For rectangular questions, consider two-dimensional data. A data set consists of points on a plane. A set of points can be shattered if every subset of the points can be enclosed by a rectangle containing exactly the subset of points and no other points. There exists a set of 4 points that can be shattered by rectangles, but no set of 5 points. The VC dimension of rectangular questions is the size of the largest set of points that can be shattered. Thus, the VC dimension of rectangular questions is 4. For circular questions, it's 3. Given the VC dimension of the set of questions, one can determine how large a sample is necessary to get approximate answers with a given accuracy with high probability. In 1964, when I got my PhD, only single gates were trained. We lacked computing power to consider networks of threshold logic units. We lacked large collections of data. The NIST data set of handwritten integers did not exist. I considered building a data set of handwritten images, but there was no technology available to scan the images. Deep learning came from an ImageNet competition. When one entered the competition, they were given approximately 50,000 labeled images from 1,000 categories and trained their algorithm on this data. Their trained algorithm was submitted to the competition where it was evaluated on a different set of images. Prior to 2012 competition, the error rate of the winner was 25%. In 2012, AlexNet reduced the error rate to 15%. Such an improvement led researchers to apply the technology in many areas with significant successes. AlexNet consisted of 5 convolution levels, followed by 3 fully connected levels, and then softmax. In a convolution level, each gate gets input from a small K by K grid, where K is between 3 and 10. There is a gate for each K by K square array of the image. The weights for each gate are identical, so each gate recognizes the same feature. There are several such sets of gates, so different features can be found. One of the items that made AlexNet successful is that 2 graphic processor units were used to train the network. The graphic processor units allowed training of networks of the size of AlexNet. In 2015, ResNet reduced the error rate to 3.6%. Humans with training have an error rate of 5%. ResNet had 1,000 levels, and this raised the issue of how to train such a deep network. In training, this appeared to require taking the derivative of an error function with 1,000 levels. This was done using a training method similar to stochastic gradient descent. Gradient descent is a method of finding a local minimum of a multidimensional function. One takes the derivative of the function and then takes a small step in the direction of the derivative, which will lower the value of the function. A version of gradient descent is stochastic gradient descent. Consider a function that is the summation of 1,000,000 terms. Gradient descent would take the derivative of each term to determine the derivative of the function. Perhaps a better process is to approximate the derivative by selecting a random sample of 100 of the terms at each iteration. This might be 10,000 times faster. Does it work? Not only is it faster, but it often finds a much better local minima. Gradient descent often stops at a poor local minima on the path it is taking to find a much better local minima. Stochastic gradient descent at each step takes a random direction and tends to stochastically seek a good local minima. Once it wanders around the region of a good local minima, one increases the number of terms selected at each step, and this reduces the variance of the path. Eventually, the full function is used to complete the search. ResNet used this concept to train a network with 1,000 levels. Taking a derivative using the chain rule for 1,000 levels will not likely work. So instead, at each iteration, randomly short out many levels and train the random approximation network. Understanding the concept of stochastic is important, since you may use it in a totally different area. Consider a 1,000 by 1,000 pixel image. For purpose of exposition, assume the image is of a cat. Consider making minor modifications of the image that would not be detected by a human, but will cause a deep network to classify the image as an automobile. Modify each pixel by a tiny amount to move the classification towards automobile. The modification of each pixel will be so small, a human will not detect that the image has been modified. However, the tiny modifications of each of the 1,000,000 pixels changes the deep network classification of the image from cat to automobile. The size of data has become enormous. One needs significant mathematical tools to process and abstract information from big data collections. We're living in an information revolution in which processing larger and larger data sets will become common. As the size of data sets increases, more subtle information can be extracted. To process these large data sets successfully requires a significant mathematical background. I will illustrate the depth of material and the need to improve undergraduate education to provide companies with the talent they need to flourish. When I was an undergraduate student, graphs could be drawn on a piece of paper and maybe had 10 or so vertices. In the 70s, graphs had grown in size to a few thousand vertices. Today, they have 10 to the 100 vertices. The number of atoms in the visible universe is only 10 to the 70th. How do you store in a computer a graph that has more vertices than the number of atoms in the visible universe? You don't. It's obviously impossible. One can explore a graph without storing it in the computer. Consider doing a random walk on a graph. All that is needed is an algorithm that, when presented with a vertex, gives the set of adjacent vertices. You can select an adjacent vertex, move to it, and discard the previous vertex. one only saves the vertex that the walk is currently at. This is just one example how data too big to store is processed. Many problems with big data involve random walks on graphs. One such problem involves computing the expected value of a function defined on 10 to the 100 values. The set of input values is so large that one cannot compute the sum directly, so one samples. But the samples are not equally likely, so one must sample according to the probability distribution of the samples. To do this, one creates a graph with a vertex for each element of the input set. The graph is designed so that the stationary distribution of a random walk assigns to each vertex the probability of the corresponding element. One can select an element by doing a random walk until the stationary probability is achieved and selecting the element corresponding to the vertex the walk is at. If the time of the random walk to converge to the stationary probability is proportional to a power of the number of vertices, the walk will never reach stationary probability. So there is a problem. An important intellectual concept is that of an expander graph, in which the time for a random walk to reach stationary probability is a function of the logarithm of the number of vertices rather than a polynomial in the number of vertices. By making sure the graph is an expander, the time to achieve the stationary probability is the logarithm of the number of vertices rather than a polynomial in the number of vertices. An expander is an important concept in analyzing big data. Data has become so large that one does not store entire data sets, but randomly samples the data. This and many other operations requires randomness. We need to understand randomness and the concept of the amount of randomness needed in a much deeper way. Let us begin with the concepts of expectation and variance. The expectation of a sum of random variables equals the sum of the expectations of the random variables. This is true even if the random variables are not statistically independent. However, the expectation of the product of random variables requires statistical independence for the expectation of the product to equal the product of the expectation of the two random variables. We shall see that because of this, two-way independence is important. The variance of the sum of random variables requires independence for the variance of the sum to equal the sum of the variances. To simplify the understanding of why independence is required, assume that the expected values of the random variables are 0. This is not essential, but it simplifies our understanding. For 0 expected value random variables, the formula on the slide illustrates that the variance of the sum of random variables equals the sum of the variance of each random variable, provided that the expected value of the product of every two random variables is equal to the product of their expected values. If the random variables are pairwise independent, the expected value of the product of two random variables equals the product of their expected values. Since we assumed that the expected value of each random variable was 0, the expected value of the summation of the product of random variables in the formula disappears, and the variance of the sum equals the sum of the variances. This indicates why, for the variance of the sum to equal the sum of the variances, does not require full independence, only two-way independence. Suppose you want a computer algorithm to generate an infinite random sequence of zeros and ones. If a random sequence is one in which there is no short description, then you cannot create such an algorithm, since the algorithm would be a short description of the sequence. So instead of generating a truly random sequence, one generates a pseudo-random sequence. If you want to randomize a set of elements by a hash function, you cannot fully randomize the set, so you pseudo-randomize the set. By pseudo-random, we mean make the set of elements appear random, but not fully random. And this raises the question of how much randomness is needed. If told to select a random integer in the range 0 to 10, and you select 5, what's random about the integer 5? There's nothing random about the actual integer 5. What is random is the way in which the 5 was selected. Thus, when we say select a random sequence or integer, there's nothing random about the actual item selected. What is random is the manner in which it was selected. Why are we interested in the way an item is selected? Usually, you're going to insert the selected item into an approximation algorithm, and we want the approximation to be close to the true answer with high probability. The distribution of the approximation is governed by the distribution from which the random element inserted into the algorithm was chosen. Consider a sequence of zeros and ones of length 10 to the 100. Clearly, the sequence is too long to store in a computer. But for an algorithm to use the sequence, one only needs a short description of the sequence and a subroutine that, given the short description and an integer I, provides the ith element of the sequence. If we want to select a fully random sequence of length 10 to the 100, we need to select from the full set of sequences. However, if we do not need full randomness, we can select from a smaller subset of maybe only 1,000 of the sequences. We refer to the selected sequence as pseudo-random. If we use the small subset of 1,000 sequences, then short names are possible. Selecting from the small subset gives us a sequence that looks random, but it's only pseudo-random. We need to determine how much randomness we need. If we only need that each bit in the sequence is equally likely to be a 0 or 1, we only need a subset containing two sequences, one all zeros and the other all ones. However, if you select one of the sequences from the subset with just two sequences, and you tell me the ith bit of the sequence, you have actually told me the sequence, and hence you have told me every bit. Maybe you would like the ith and jth bits to be statistically independent for all pairs I and j, but you do not need triple sets of bits to be fully independent. Telling you the value of 2 bits might determine the value of a third bit. Consider the following set of 4 sequences of length 3. The 4 sequences are two-way independent, since in my telling you any bit in a sequence does not change the probability of any other bit in the sequence. To have full randomness, you would need to select a sequence from the full set of 8 sequences of length 3. The reason we may be happy with just enough randomness to have two-way independence is that when we have a random approximation algorithm, we would like the expected value of the answer to be the true answer and the variance to be small, so that the actual answer would be close to the true answer with high probability. To determine the variance of a sum of random variables, we would like the variance of the sum to be the sum of the variances of the individual random variables. This will be true if the variances are statistically independent. However, we do not need full independence of the variables. We only need pairwise independence. Assume one owns thousands of stores located throughout the world and would like to know the number of customers. When a customer makes a purchase, a record is received which includes a credit card number, a WeChat account number, or some other identification of the customer. We could keep a list of distinct customers, and when a customer ID is received, compare the ID with every ID on the list. And if it's not found, add it to the list. This method is extremely slow and not possible if you have billions of transactions. There are many other methods, but I would like to illustrate a very efficient algorithm which gives a very good approximate answer to the question, how many distinct customers are there in the set of stores? Let M be the number of potential IDs, and let D be the actual number of customers. The expected distance between the IDs is M over D plus 1. And let min be the smallest ID received. Solving min equal M over D plus 1 for D gives the number of distinct customers, D, is equal to M over min minus 1. Thus, we only need to keep track of the smallest ID to get an estimate of the number of customers. How accurate is this estimate? The argument assumed that the IDs received were random. However, that may not be true, resulting in a misleading estimate. The solution is to randomize the IDs. Then with high probability, the minimum ID will be between M over 6D and 6D over M, giving us a good estimate of D. Establishing that the lower bound on the probability is small does not require that our randomization of IDs is pairwise independent. However, establishing the upper bound is small requires calculating a variance and hence requires that the randomization is two-way independent. Recall that two-way independence means the value of one element gives no information about any other element. Almost every approximation algorithm an analysis shows that two-way independence is the most randomness that is necessary. Ravi Kannan and Avram Blum and I have documented much of this material in the book and negotiated an agreement with the publisher that we could give a digital copy away free to anyone who wants it. It can be accessed from my homepage website. It's used at a number of universities at the sophomore or junior level. It's important that students master this material early in their university education so that they can use it as they take more sophisticated courses. At this point, I trust I've illustrated the mathematical sophistication necessary to effectively handle big data. In order to produce the talent essential for companies to successfully process big data, we need to improve undergraduate education. There are many other areas such as AI, cryptography, security, and quantum communication that also require sophisticated theory. To handle all these areas will require improved education. I would like to spend a few minutes discussing a project the Minister of Education in China created to improve computer science education at the top 33 universities in China. This project has become known as Project 101. And PKU's president, is in charge of it, and he has assigned individuals to execute the plan. If it's successful, it will be extended to other domains and more institutions. It's a very ambitious and important project. It consists of two major components. The first is to determine the key courses in computer science and develop the content and teaching material for them. This component will actually improve computer science education at all 1,500 universities in China. The second component is to improve the quality of teaching. For the first component of the project, the 33 universities selected 12 key courses in computer science. Each course was assigned to one of the universities to develop content for the course. The individual at the university responsible for developing the content for an assigned course formed a team of the top 10 faculty in the area of the course to work on developing the content and teaching material. Improving teaching. The second component of the project focused on helping faculty improve teaching. This methodology grew out of a project to evaluate teaching in which a faculty member sat in on a lecture and observed the interaction of the faculty member teaching the course with the students in the course. When evaluating teaching, one learns information that can help the professor teaching the course improve his teaching. This is key. Let me illustrate by telling you what I learned in evaluating one class. The faculty member was an outstanding young faculty member and was teaching 30 students. When she started, every student was engaged and listening carefully. About 30 minutes into the lecture, half the students disengaged. I wondered why. The faculty member had just put up a mathematical theorem and then spent 20 minutes proving the theorem. I talked to the faculty member after the lecture and told her what had happened. We discussed it for a while and concluded that maybe the students did not understand what the formal mathematical theorem said. And it might have been better if she had explained the theorem intuitively, why it was important and how it would be used. She could then have engaged the class in converting the intuitive form of the theorem to the mathematical theorem. Also, we discussed if it made sense to spend 20 minutes proving the theorem. Maybe just discuss the key steps that would be needed. This led to a discussion what we would like the students to remember about the lecture 6 months from now. It's not the detailed formal proof. Based on this experience, Project 101 is having faculty sit in on lectures and discussing how students interacted with what their teachers taught. The assumption is that the resulting discussion will lead to improved teaching. AI systems will play an important role in the future and will be the main contributor to the gross national product. Talent will be important for the development of these systems. Regions that develop talent will attract companies that will grow the region's gross national product. Developing the talent will require improving undergraduate education. And this will require changing the metrics by which universities are evaluated. It's not the amount of research funding a university attracts or the number of papers published, but the quality of undergraduate education. AI will create many social issues, and resolving the issues that arise will require quality university educational programs. This means that a quality education in science or engineering needs to include the humanities and social sciences. Another important issue concerned about improving the quality of education is educating the general population to the importance of education. When communicating a message, it's important to understand who the audience is and what you want them to remember. A scientific researcher talking to other researchers working in the same problem area can use technical words and give theorems and proofs. A scientific researcher talking to a general scientific audience should instead explain intuitively what he has done, why it is important, and how it will impact the field. An individual speaking to the general population needs to confront another issue, which I will illustrate by a short story. I became aware of the impact of the first 3 years of a child's life on their future life and looked at research on this issue. Today, there is scientific research on how the brain develops and on the impact of the intellectual environment of the child's first 3 years. In the first 3 years of a child's life, the brain learns how to learn. Experiments 30 or 40 years ago helped mothers provide a stable, intellectually rich environment for the first 3 years of their child's life. And then 30 years later, compared the child with others who had not been given such an environment. The results were impressive. There were fewer mental issues, higher educational levels, higher salaries, and other significant benefits. The first 3 years of a child's life is so critical that I wanted to educate and build support for funding a program so every child would have a stable and intellectually rich environment for their first 3 years. When engaged in developing a plan to educate the general population, I discovered that a writer for a major magazine only received $6,000 or $8,000 for an article. I realized I could hire 10 high-quality writers. But there was a problem. How do I identify quality writers in the child care area? So I contacted the individual who selected writers for a major magazine, told him what I wanted to do, and asked for his help in identifying writers. This is when I learned a major communication issue. His response was, "John, that's a dumb idea." He got my attention, and I asked him to tell me more. What he told me was that over half of the US population never read an article in any of the magazines I was talking about. He said I needed instead to develop a digital channel and communicate that way. I thought about it and quickly realized that was not going to work either. The general population already has acquired their beliefs on issues, and they're hard to change. What I should focus on instead is improving elementary school education. Before moving on, I should tell you about a conversation with a researcher who is focused on understanding what made an intellectually rich environment. I mentioned it must be hard to do research if you need to wait 30 years to see the result of an experiment. She said that is not what she does. She told me that the brain of a mouse develops similarly to the brain of a human. So she uses mice as a proxy for humans. She purchases 200 mice, puts 100 in ordinary cases, and the other 100 in cases with an intellectually rich environment for 3 weeks. Then she puts all 200 mice together for 2 years and tests them on mazes and other tasks. The 100 mice that were in an intellectually rich environment clearly outperformed the other mice. I then asked, what's an intellectually rich environment for a mouse? She emailed me a photo where each item was labeled with a note telling me what part of the brain it developed. I mention this experiment since it's an experiment anyone can repeat and is very compelling. Consider educating the general population about global warming. You start by teaching global warming to second graders. You have a globe of the world, and you tell students it rotates, and for the portion facing the sun, it is daytime, and for the other portion, it's night. You mention that we can see the moon since some of the light from the sun reflects from the moon. Then you mentioned that when the sun shines on the portion of the earth that is day, some of the sun's energy is conserved and some is reflected. If the ratio of energy that is conserved changes, it will have an impact on the Earth's environment. At the present time, the ratio of absorbed energy is increasing, and that is called global warming or climate change. In subsequent years, more detail is taught. To understand what I will discuss next requires understanding the definition of basic and applied research. The terms basic and applied do not refer to how fundamental the research is, but rather they refer to why one is doing the research. Applied research is done to solve a specific problem. Basic research is research on an issue that someone is curious about. There need not be any application. Applied research is unlikely to produce fundamentally new research directions since it's focused on solving a specific problem. On the other hand, basic research goes off in all kinds of different directions and sometimes creates a whole new area which leads to new industries and millions of jobs. The funding of basic research in the US universities was one of the best investments ever made. If the mission of a university is to educate the next generation of talent, why do departments in science and engineering focus on hiring researchers? The answer is actually very simple. When a university hires a new faculty member, they're hiring someone for a career of 40 years or so. They want someone who will grow with their field and 30 years from now will not be teaching material that is 30 years old. They want someone who, because they're curious, will observe how the world is changing and how that should change education. Thus, they are looking for two aspects of a potential faculty member. Is he curious, and does he appear to have lasting energy? If the potential faculty member is curious and a new direction appears in his field, he is likely to explore it and update his course. This will keep the faculty member teaching material that is new and up to date. Unfortunately, many recruiting committees look at the candidate's research and ask how fundamental is it? And they look at how important are the journals he publishes in. They should instead be asking, why did he pick the topics he has worked on, and how curious is he? Will he continue to explore as he gets older? Since my time is running out, let me just say, for those of you in the audience who are just beginning your careers, choose a career that you really enjoy. You get only one life to live, and you should enjoy it. It's been a pleasure to speak to you today, and thank you for giving me this opportunity to share my ideas. Thank you.
Thank you so much for the great speech to share the effort of China in creating the talent necessary to be a leading nation in the information age. I deeply sympathized with how important it is to create high quality talent for the information age, and I realized we should do more for high quality talent fostering. Let's give him a big round of applause again. Due to time constraints, so let's take only one question on site. No question? Sung-Young, did you check the online Q&A? Okay. No question? David? Okay.
David Ryder, Google Research in New York. I've had a lot of discussions recently with colleagues about how to design graduate education in the age of ready-made models or pre-trained models that can be used and where students are pushed to publish a lot of papers that beat the state of the art, that do well in leaderboards, but it's not necessarily clear what the fundamentals are that they need to learn in order to be successful researchers going forward when a field like natural language processing, where we work, changes so fundamentally every few years. I'm wondering if you have insights to convey in terms of graduate education and the important fundamentals in computer science.
Yes, the first thing I would mention is that publishing papers is irrelevant to graduate education. What you want to do is educate the student to be able to process the material that's available. When I was in elementary school, high school, and college and so forth, I was taught facts, but that's no longer necessary because you can get the facts on the internet. And what you need to be educated is how to process the facts and how the field is evolving. And the most important thing for a graduate student, though, is to find out what they're really curious about and explore that. Several of my graduate students have got Turing Awards. And one of the reasons is when I asked them what they wanted to work on, and they mentioned something, I didn't think it was very important. But nevertheless, I told them, go ahead and follow it because they were curious about it. If I had told them to do some work on something that I was interested in, they probably would not have been successful. So what graduate students should do is they should find an advisor who will let them follow what they're really curious about. Because you're not going to necessarily do something fundamental while you're a graduate student, and that's not the purpose of getting a PhD. The purpose is to follow things you're curious about and learn how to explore. I don't know if that helps you too much, but whatever you do in your career, do what you enjoy and what you're curious about.
Thank you.
We'll wrap up here due to time constraints. So thank you, Professor John Hopcroft. This is the end of keynote speech. Now it's time to conclude. Let's invite Professor Seung-Hwan Lee, General Co-Chair of this summit, to give closing remarks.
I would like to thank you, all of you, for attending the event until the end. During the two-day event, I hope it was a fruitful time for everyone attending here. I hope that talks and discussions helped your research improve, and eventually, I wish it will lead you to make opportunities for cooperation in research and foster human resources among domestic and foreign researchers. See you next year. Thank you.
Thank you, Professor Seung-Hwan Lee, for the closing remark. And all the effort to organize the Korea AI Summit 2022 successfully. The Korea AI Summit 2022 was held under the theme of AI for Good. It was meaningful that global top-notches share the advanced technologies here. Also, we realized how AI technology can empower and enrich humanity and our lives. Finally, we sympathized that we have to put all the effort to cultivate high-quality talent to power the nation under the information revolution. I hope we exceeded your expectation through the two-day program. That brings us to the end of the Korea AI Summit 2022. Thank you once again for your attending. Goodbye.